is localized methods for diffusions in large graphs, and this is basically two pieces of work, one with Kyle, who's out in the audience, and the other with Michael Mahoney, who's out in the audience somewhere. But it's really about something else. And so there's, in some sense, two types of people in the world. So there's the red pill people, and then there's the blue pill people. And so what are these in this case? Well, so the red pill people are the people who believe that everything ought to be explained by matrices. And the blue pill people don't believe that, and so they can just ignore my talk. So in this talk, we're going to explain everything in terms of matrices, and we're really going to use matrix methods as a proxy for graphs, which means we get to introduce ourselves to these two people. So this is Golub and Van Loan, and these people talk about matrices. So if you haven't read the most recent edition of their book, they've got all sorts of great things in there. All right, so I said we're going to talk about matrices, but I should at least introduce a little bit about what a graph diffusion is, or I would think of this as also a matrix equation. So in a graph diffusion, we've got some type of graph object here, and we're really not going to look at that graph. We're going to look at a stochastic transition operator on that graph. So this is a column stochastic matrix P that's equal to the adjacency matrix times the inverse of its degree matrix. So this is something like propagating out your average, or sorry, you're propagating out something like an average of your value to all of your neighbors. And what a graph diffusion is we take some, this actually, that doesn't really show up enough. So we take some seed S, and so what should you think of S? S is going to be a really sparse vector. So think of S as having 1 or maybe 10 non-zero entries. So this is representing something over the nodes of our graph, and we're distributing whatever is in S throughout our graph. So here we've got whatever the orangey color is sort of spreading over that region of the graph. And how does it spread? Well, we're just going to take a series expansion. So we're going to take a weighted sum of P to the K. So alpha here is how much, or sorry, alpha sub K is how much we're going to weight a path of length K. Where do these problems show up? So graph diffusions help when you're doing attribute prediction in a social network where you only have some of the nodes labeled. You can use the diffusion to try and estimate what the others are. It helps in community detection, which is really the problem of finding small conductance cuts, so we'll see a little bit of that. This has to do with local Cheeger inequalities and all sorts of other beautiful mathematics that we won't have time to get through. But it also shows up in ranking. So one of the things we're going to spend a lot of time looking at is the PageRank diffusion. So if you're a matrix person, you might recognize this as related to the resolvent function of a matrix. Here we're just going to look at it more like a geometric series, or equivalently solving a linear system. At the end of the talk, we'll also see a little bit with the heat kernel diffusion. So there's been a lot work done over PageRank over the last 10 or 15 years. There's been less work about the heat kernel, but we'll sort of illustrate that maybe people should be spending a little bit more time looking at the heat kernel than PageRank. So what is the sort of characteristic difference between these two diffusions? So here what we're looking at is how much of a weight the different diffusions place on paths of length K. And so the two blue lines are illustrating what PageRank does. So this is just a geometric series. So at every step, you get less weight on the next path. With the heat kernel, it's actually more interesting. It sort of focuses you in a narrow region. So this is related to the matrix exponential function. But the heat kernel for various versions of these parameters, and I apologize, that's supposed to say beta, not alpha there for the PageRank case. They just have very different behaviors. However, they both share somewhat of a common property, which is that when S is really sparse, in a lot of real-world networks, the expansion of these diffusions has a property we're going to call localized. So when you compute one of these things in a graph with, say, 5 million nodes here. So this is the live journal graph, which we heard that our phones can do this morning. So I don't want to pretend that this is a big graph, but it's a nice graph to illustrate these things. What happens when you just compute this, say, in MATLAB, and then you plot your solution vector x? Well, we have 5,000 nodes represented, sorry, 5 million nodes represented on that horizontal axis, but there's only about 2 large entries there. If you do a slightly more refined analysis and you sort that vector and then look at how much of an error we get if we just take the largest k entries of that vector, what do we see? So this axis is logarithmic. So when we go from here to here, we're actually adding another million non-zeros to our vector, whereas when we go from here to here, we're adding 10 more non-zeros. So if we have about 1,000 non-zeros, we get about a 10 to the minus 4 approximation of that vector in a 1 norm. And so this is basically what we mean by a localized vector. It's a vector that you can approximate to a reasonable degree of accuracy with a very small number of non-zeros. Now, the mission in this sort of talk is to find solutions of these diffusions in work that's proportional to the localization of that vector. So we want to find the solution in work 1,000, not work that scales like the size of the graph. So not work 5 million, but work 1,000. So there are sort of two types of localization. Most of the talk is going to focus on what we're going to think of as an entry-wise localization metric. So that this involves what do you call a good approximation of this vector. So here it's an infinity norm, and it's actually an inverse degree weighted infinity norm. So if you have a big graph and you have a very large degree node, in this metric you do not need to approximate that entry very accurately. The other entry, or the other kind of localization is going to be uniform, where we basically need to approximate the entire vector to a prescribed accuracy. These things tend to be much harder to prove than these things. So there have been a number of results along this form in the literature. And so we have sort of 4 extensions of these. So the first is we're going to give a new interpretation of the PageRank diffusion in terms of its relationship with min-cut problems. The second and more important thing is we're going to give a new understanding of the scalable localized PageRank push method. So this is a method that's been known to give an entry-wise localized solution, but it wasn't really clear exactly what it was doing. It had a tolerance parameter that people would set to 10 to the minus 3, and it would give you localized solutions. We're going to give a much more refined analysis of that. And then we're going to take the same analysis, or the same ideas, and generalize them to the heat kernel as well. For more about uniform localization, please do see Kyle's poster on Thursday. He's going to talk much more about that than I'm going to have time for. So first of all, and just as an advertisement for Kyle's talk, so here was that sort of uniform localization plot we had. So Kyle and I have been working on algorithms that basically track this curve exactly. So as we're varying a tolerance parameter in these algorithms, we trace out almost exactly the same curve. We have a few more non-zeros than the exact algorithm does, but we get pretty close. All right, so let's go through a little bit about PageRank and min-cuts. So I think we've heard a little bit about the PageRank vector already, but there's all sorts of different interpretations for it. The most common of which, and most or what a lot of people like, is the random surfer idea, which is that the PageRank vector models a random surfer that, with probability beta, follows a link in the graph, and with probability 1 minus beta, it does something else. In this case, doing something else means you jump according to a distribution S. So this is your seed. So you basically return to your seed with probability 1 over beta. And the goal is to find the stationary distribution of this random walk. Well, it turns out that it's equivalent to a linear system in this case. So we can just solve this linear system directly, or we can evaluate it by the series expansion. We're going to look at undirected graphs here, which is sort of a strange case to look at PageRank in. But there's a lot of good reasons to look at PageRank and undirected graphs with these seed nodes, because the PageRank vector really says where that seed sort of expands in that graph. In which case, we can look at a different normalization of the PageRank vector where we just scale by z, or sorry, by d inverse, and we can solve the system with the Laplacian matrix of the graph instead. All right, slight aside here, but the st-min cut problem in a graph, we're going to state as follows. In an st-min cut problem, we prescribe a node S and we prescribe a node T, and we want to find the way of separating S from T in this graph by cutting as few edges as possible. And so we can write this as a one-norm optimization problem with the unweighted incidence matrix. And if our graph did have weights, we wanted to minimize the sum of the weights, we could use a diagonal capacity matrix to basically scale that norm. So C would be a diagonal matrix with all positive elements. If you like summation expansions, this is really just a sum over all edges of the sort of weight of the edge times the difference in the vectors. This is an easy problem to solve. There are great algorithms to solve it. In the unweighted case, you can solve it via max flow. In the weighted case, you can do network simplex. Or if you work for an industrial optimization company, their codes usually run faster than network simplex does, even though they have worst case exponential time. All right, so we're going to relate PageRank with st-min cut, and the way we're going to do it is through this particular construction we call a localized cut graph. So this was inspired by a whole bunch of work in the literature, including the flow improve method of Rita Anderson and Kevin Lang, and then a recent construction by Rekia and Zhu on doing flow improve in a local sense. What we're going to do here is we're going to take our undirected graph, and we're going to add in two nodes, S and T, and we're going to prescribe a set S. So set S is going to be something analogous to that seed vector we had initially. But we're going to link up the node S weighted by alpha times the degree vector here. So if this node here has degree 4, so when we connect this node to S, we weight it by 4 alpha. And we do the same with all nodes not in S. We connect them to T with weight of the degree times alpha. So the new matrix has an adjacency matrix where things are just scaled by the degrees. So if we take this matrix, we can write down the new incidence matrix of this graph, and we can state the st-min cut problem on this new graph. And now when we want to go for PageRank, all we do is, you see that little 1 there? So we change that 1 to a 2, which means instead of looking for a 1-norm approximation, we're looking for an ST electrical flow or a 2-norm type cut problem. And lo and behold, the solution of this, so the solution of this 2-norm cut problem ends up being exactly our PageRank vector in the Laplacian form. So it ends up getting scaled by a small factor there, but that's sort of incidental. So again, underlying PageRank is this st-min cut problem. However, we can actually go so we can construct an st-min cut problem that gives rise to a particular PageRank vector. We can also go the other way. So if you have a PageRank problem that you want to state, you can create an st-min cut problem for it. So in the previous construction, we had this weird thing where you had your set S, and you sort of used the degrees to connect it up to S and T. So what would happen if our seed was the uniform vector over all nodes? Well, it's not sort of clear how we would connect that up to S and T from that particular construction, or what your set S would look like. Turns out there isn't a set S there. We have to generalize this a little bit to a vector form. But what we can do is just note that what we, in some sense, what we needed was to add a total weight of alpha times d to every single node. So we need to add alpha times the degree, total weight of edges to every single node. That gave us the scaling on the diagonal. Sorry, I apologize. I sort of skipped over that on the last slide. But what that means is if we did have a uniform vector, we can connect S to everyone in the graph with weight alpha. And then in order to maintain that degree invariant, so we want to add alpha times the degree, total new edges or new weight to every node, what we do is we just add the remaining degree, so the degree minus S, to T. So we basically take all the residual and use that to link up to T in order to get the degree that we need. And if you solve this system, if you do the same machinery with this system, you state the 1 norm approximation and then take out the 1 and turn it into a 2, you get back the PageRank vector with uniform teleportation as well, or a uniform seed. So PageRank implicitly approximates the solution of these ST-min cut problems. Let's go a little bit further. So there's a common algorithm that people use to solve what are called personalized or localized PageRank problems, or estimate these PageRank diffusions very efficiently. And it's called the push method. So it dates back, I mean, the version I'm going to give is due to Anderson, Chung, and Lang, but it goes back much before them. So it was also proposed in very similar form by Frank McSherry and Jay and Weedham. Again, I'm a matrix guy, so it turns out that this is really just a particular version of the Gauss-Seidel method, although most people would never explain Gauss-Seidel this way. If you do want to see a little bit more about that, I've got a talk online that was recorded at the Simons Institute last November on that. We don't have time for it here. They derived it to show a new runtime on balanced solvers of Laplacian systems, but let's just look through what happens here. What you do in this method is you're trying to compute a PageRank vector where your seed S has just a couple of non-zeros in it, think 1, and you want to do it without looking at the entire graph. And so what this method does is at every step it maintains a solution vector and a residual vector. So this is really the residual of the PageRank linear system. And it picks a coordinate and basically takes the current residual and adds it to the solution. So this is exactly a relaxation step if you're used to matrix algorithms. What it does then is it then updates the residual, which involves modifying all the neighbors of that node. So it's called push because it has this interpretation of sort of squashing your current residual and distributing your mass out to your neighbors. And so what this looks like is you squish that node in the middle, and then it created A, B, and C. You squish B, and it creates 3 new nodes. You squish C, and it creates a couple more nodes, but then gives you a little bit more mass there, and you just keep exploring the graph in this very local way. So why do we care about push? Well, so one reason it's been used for lots of different studies in the literature. So it's used to investigate communities in large networks. The more theoretical reason is you can use it to derive a local Cheeger inequality. So we heard a little bit about Cheeger inequalities from Yannis Koustis yesterday. What this does is it gives you something similar, but in a region of the graph that's nearby your seed. So in a large graph, you might not want to look at the entire thing. This gives you a much more refined understanding of it. Some people think you can use this to do fast personalized PageRank approximation. That's actually not not the best use of it because you get an approximation that's in actually a degree inverse weighted norm. So this isn't particularly useful for saying you've got a good PageRank vector. You get a good estimate of some type of scaled vector. But you can do this I meant an entry-wise localized way here. In order to attain an accuracy of epsilon in this sense, you only need to look at 1 over 1 minus beta times epsilon edges independently of the size of your graph. So what you have to do here doesn't depend on how large of a graph you're looking at. It only depends on beta and epsilon, which makes it very nice to tackle incredibly large networks. So in particular, if you look at this, if you look at what the push method does, if we solve it on a fairly small graph, it ends up being 0 on most of the vertices here. So it keeps these solutions sparse. So we wanted to understand a little bit about this. Is this just an algorithmic property, or is there something deeper going on with this method? Our intuition was that there was something deeper going on with it because it works remarkably well. When something works remarkably well and it shows up in all sorts of different places, it's a sort of hint that the algorithm might not be the end of the story. Turns out it's not. So there's a precise characterization we can give to an approximate solution from the push method. So the push method contains a tolerance parameter, tau. And so if we just run the push method with the tolerance tau, and we look at it with one of these degree-weighted seed vectors, then we can show that the push method with tolerance tau tau might be something like 10 to the minus 3, a very coarse tolerance if you're used to solving a linear system. That solution exactly satisfies this one norm regularized sort of electrical flow or two norm cut problem. So it's not like we're, so in this sense, what we're doing is precisely characterizing the output of this approximation algorithm, or of this approximate diffusion. Now, the proof of this isn't very interesting. If you simply write down the KKT conditions and show that the previous algorithm satisfies them. So insight 2, the PageRank push method implicitly solves this problem. But I'd say in light of some of the questions yesterday, there's actually another insight here too. So there's insight 2 prime. So if we're solving PageRank with the push method, we only get about 3 digits of accuracy. But we can also get 16 digits of accuracy on P prime. So if we look at that other thing, we are exactly solving that second equation. So what we're doing is, instead of thinking about the original problem as the goal, we can think about this revised problem as the goal and show that push is actually a very precise algorithm on that problem. I was going to go over a little bit about how push helps identify the right thing with sparsity. I'm running a little bit low on time, and I don't think this is the most interesting thing, so I'm going to skip to some of the work on the heat kernel. Sorry, there's one other thing I wanted to mention. So we were trying to figure out what exactly to call these new results. So what we've been doing is we've been taking an algorithm that people have used extensively, this push method, and trying to reinterpret it as something new. Not something new, but recast it as achieve some type of deeper insight into why it's so successful. And so we coined the name algorithmic anti-differentiation for this. And so this is an activity that's actually quite common in machine learning. So what happens a lot is we come up with these schemes, and effectively you're trying to solve some ill-defined problem like find communities in a network. And so you spend a lot of time working on this, and after some point in time, you figure out a heuristic that tends to do well. So in this case, one of the heuristics for finding communities is just run 3 steps of the power method. So just take p to the third times the seed vector, and this gives you a reasonable estimate of communities. So why does this work? Well, that's not entirely clear. It is clear it gives you good empirical results. But what you would do from an algorithmic anti-differentiation perspective is you try and say, what does that procedure, 3 steps of the power method, exactly solve? And so this is a problem Michael Mahoney and Lorenzo Arricchia looked at one point, and they showed that this algorithm, 3 steps of the power method, is a particular type of regularized diffusion. And they characterized exactly what the regularization implicit in that algorithm. So it's not like when we're doing push and this 3 steps of the power method, our ostensible goal was not to solve these regularized problems. These are all sort of implicit or sort of hidden features of these algorithms. And a lot of times it's actually these hidden features that are key to understanding why they work on much larger data sets. So some algorithms work when you scale them up by a factor of 10 or 1,000. Other algorithms don't. And a lot of times it's these insights you can get by sort of taking a heuristic, trying to see what it's actually doing in a hidden sense, and using that structure to predict whether or not it'll work. So just as one instance of why this matters, so we were looking at a problem of semi-supervised learning, and it turns out a lot of the same ST-min cut ideas can apply to most of the diffusions that people study in semi-supervised learning. This is the problem where you're given a graph, and you're given a couple of labeled nodes of this graph, and the goal is to predict the other, or the labels on the unknown node. So here we have a bunch of digits. We're linking up digits if the images are close by. And we have one node labeled with the digit 1 and one node labeled with the digit 2. So most people, I think, would say that these 2 nodes in the bottom ought to be 2, and the top 2 nodes ought to be 1. And the semi-supervised learning problem on graphs is just a formalization of all of this. Well, if you take a standard algorithm out of a paper and run it on one of these problems in a parameter regime the authors hadn't considered, what you would do is you would get error rates that are about 0.9. So this is a 10-class prediction problem. And basically what this means is that your algorithm is worthless. You're not predicting anything of any type of accuracy at all. And there's a couple of different variations of this. But what you get out of our method is these diffusions are related to cut problems. So they're related. So we've got a relationship between numeric scores and cut problems. And what we heard from Yannis was that when you want to understand how a spectral or numeric approximation of a cut relates to the underlying cut, what you need to do is sort the vector. So you need to use the sort or the order, the rank of those nodes in the vector as opposed to their explicit values. So the difference between this plot and this plot is in this plot we were using the values of the diffusion. So how much like a given node are you in order to predict the class. Here we're using the insight we get from our cuts, which is that the order of the nodes is much more important than the values. What we see here is that there's basically no difference between any of these different methods, and all of them have reasonable accuracy. Whereas when we use values, we get unreasonable things. All right, I have 5 minutes left. Okay, good. So recap so far, we've used the relationship between PageRank and mincut to get a new understanding of this push method. And we've used this insight to actually improve semi-supervised learning problems on graphs. So is that the end of the story? Is this just a PageRank thing? Turns out no, we can do the same for these other diffusions as well. So here we're going to look at the heat kernel diffusion. Why do we care about the heat kernel diffusion? Well, by and large, any property that people have associated with PageRank ought to hold for the heat kernel as well, except it'll hold in a slightly different sense. So if you're getting good results with PageRank, you might want to try heat kernel, or you might want to try some other type of diffusion as well. But the question is, can we take these high-performing algorithms like push, which works on just massive graphs, and use them to look at things like the heat kernel? The answer is yes. So the heat kernel also, just one particular instance of that is the heat kernel satisfies a local Cheeger inequality just like PageRank does. What wasn't known for a while for the heat kernel was any way of actually computing it efficiently in a large graph. So there were matrix algorithms that would do repeated matrix multiplications or a Lanczos procedure, but these don't scale to billion node graphs all that easily. So we have the first deterministic algorithm to do these in large graphs. And what does it involve? Well, it basically involves taking that matrix exponential and turning it into an even bigger linear system of equations. So here, what we're doing is we're taking just a simple case with t is equal to 1 in that diffusion. So we take the matrix exponential, we write out its Taylor series, and then we cook up a big linear system to basically evaluate the Taylor series. And what we can do is we can tie approximations of this big linear system back to approximations of the heat kernel. This gives rise to a single column code that you can implement. So I don't expect anyone to read here, but this is just what a real implementation of the push method for solving that linear system looks like. So the push method works on almost any linear, or sorry, it works on linear systems of this form. And so this is what the code looks like. It satisfies a slight entry-wise localization result like the push method for the PageRank vector. And we have a little slight bound on n here. But this method works in extremely large graphs. So here are some of the runtime numbers we get where we look at graphs with the sum of the nodes and edges between 100,000 and up to about 1 billion here. And what this algorithm does is it runs in about a second on a 1 billion edge graph. Or if you're a matrix person, you would prefer the non-zero count. So this matrix has 3.6 billion non-zeros in it. And this method runs in approximately 0.8 seconds on such an object. How does it run so fast? Well, it doesn't actually need to look at all the matrix. So that's why it's like, it's not really running on a 3.6 billion node graph. It's a much smaller graph. More recently, we've run this on the entire clue web graph, which is 72 billion edges. And on that, when we run it on one of our servers, it takes 99 seconds to load the graph into memory, and then it takes exactly 1 second to compute the result, which has 36,000 non-zeros in it. So I'm out of time. Here are a whole bunch of references and some going work. But all of our code is available, so if you want to play around with any of these diffusions or insights, that stuff is all there. And the papers are all on my website, too. Thank you.